Okay, I think we can start then. Pedro is here, Gaston is here, Jordan is here. And so, at least today, one of the main goals is to give a very famous application of the finiteness of Cartier crystals. This is strong finiteness result we've been talking about, that it's related to the existence of test modules. It's the following theorem. This is a very, very famous theorem of Gennady Lubeznik that you may have heard of. So it's much bigger than this, but the one that we can state easily is the following one. So suppose that you have a regular ring over Fp. Okay, let's assume with the finite, the proof we're going to give only works in this case. But I think this works even if R is not a finite. But yeah, so this is the setup. And so we can give an ideal of R. And out of this, we can construct local cohomology modules. Right? And so we know that these things are Artinian and far from Noetherian. However, even if they are not Noetherian, they seem to enjoy many finiteness properties as Noetherian modules do, or finitely generated modules do. And the thing is that they have finitely many. So let's say, so the theorem is that it has finitely many associated primes. Okay, and so this has been a very famous result, and there are many variants that people have keep studying this. So this sort of theorem is still an active area of research that you can get into. The other thing, for example, you will see here is that these modules have finite Bass numbers, if you know what they are. We haven't defined them in class, but it's part of the same sort of theorems here. And so the goal today, so we won't use this for anything in this course, I think, but I would like to sketch a little proof of how this is a consequence of the finiteness result for Cartier crystals. Okay. So the thing is, the moral of the story here is that for regular rings, we can be very explicit about what the category of Cartier crystals is like. Okay, but that only works. The only works for regular rings. So for today, we can say that we're going to assume that R is regular essentially. So the proof of this is actually very rich, and there is a whole bunch of very nice theory attached to this. But what we're going to do is we're going to take the minimum we need to do this. Okay, even though there is like a whole bunch of things behind it. Maybe later, if I teach the course a second time, I'm going to add everything. Actually, my plan was to add the whole thing because the thing is beautiful. But I don't think we have time for that. So the minimum is the following. So what we're going to need is, so first of all, we're going to describe very explicitly the category of Cartier crystals let's say C crystals over R, regular definite ring. So this description is due to Manuel Bicla and Buckler. Okay, so, and here C is gonna be the free one, the free a key algebra generated one operator. So okay. And so to do so, we need the concept of Liu-Bestic module. So well, the notion, and speaking, is the notion of, we need to make the notion of Liu-Bestic finite. So, as you can imagine, this is not a very nice term for what we do here, because it doesn't have much to do with F-finite rings, or it's a different thing. So, the site is like the same. I'm just going to call them Liu-Bestic. Liu-Bestic module. So today is the only day in which we're going to study this concept. So just for today, we're going to call them Liu-Bestic module, so that we avoid any confusion with the finite rings or anything along those lines. Okay. Okay. Yeah. So you remember that the other day we were talking about F modules, and actually in his paper he introduces a notion of F module, which is completely different to the one we're doing here. But yeah, so the terminology is not very good. So we're going to just call them Liu-Bestic module. So what is a Liu-Bestic module? So so for this, we're going to take R. We're going to assume R to be a regular ring. So for the definition and the finality, we don't need this. We don't need R to be regular, but we want to have a nice concept. Somehow the regularity is very important. That's a nice pen. Is it the, what isn't it? Something lemon? Oh, I see. That's a very cool. So, and what we're gonna take next, we're gonna take N to be a finitely generated R module. In the theory, this is often called a root, I think. The root of the Liu-Bestic module. So we're gonna start with this, and we're gonna start with gamma. It's gonna be a map from N to the Frobenius pullback of N. And of course, it's an Erlanger map. And so the point is that with this data, we can iterate this, right? So for example, we can start here with N, then map to the pullback, the gamma, and then we can take the pullback of gamma, which is gonna go from the second pullback here, the pullback along the second iteration of Frobenius. Okay, let's move it a little bit. And then we can continue, right? Then we can take the second pullback here. So here we're going to have the first pullback of N, and so on. Okay. And so you have this system, and out of this, you can take the limit. I guess it's a colimit. And that's going to give you a module that I'm going to denote like n, like math cal n, calligraphic n. And the gamma also converges to the limit. But I'm just going to call gamma 2 by use of notation. I guess in the literature, it's also called theta very often. You would see that they start with a root. They use this iteration, they take the limit, and they get this structure here. And so, what is the point here? The point is that when you take this limit, right? Well, it is the limit of iterating this, right? So the point is that if this is an isomorphism, well, the limit is going to stop because there's a whole bunch of isomorphisms, right? So what you want is to start with this structure and to make it an isomorphism. And that's going to happen in the limit. So the point is that this is an isomorphism by pure abstract nonsense. I'm going to put as an exercise. Okay? And that thing you have there is what we're trying to define here. So this object here is a Uvesting module. Okay? So a Uvesting module is the following. So intuitively, or another way to say the exact same thing is that a Uvesting module is module n with a map from it to its Frobenius pullback that just happens to be an isomorphism. Okay? And that is obtained from a finally generated source. Okay? By taking this limit. So here is, I just put it as a remark, but it's an important remark. You may want to do this if you have the will. Remark. So as I was saying, the definition doesn't require R to be regular at all. It doesn't matter. You can just define it for whatever ring you want. But the point is that since R is regular, what do you think is being used here? That this pullback is a flat operation. So i.e., Frobenius pullback is flat. Well, actually, yes, it's a projectile. It's flat. So then, Uvestic modules, but the point is that they form a category, right? Like you can imagine what a morphism is going to be, right? Like you're going to have a map from here to another one, and what you want is a commutative diagram that is compatible with this structure, and so on, right? So the point is, like, they would form a category inside the category of our modules. This is the point, and this is going to be a full set. Well, it's going to be a set subcategory. What does that mean? It is going to become a full subcategory that is closed under extensions. And for example, this is the sort of thing you may localize a lot. Okay? But this is you can try this as an exercise, it's optional. The whole exercises are optional, really good. It's a bit harder, but it really relies on this. And so the whole remark I want to make is that regularity is used to get a nice object. Okay? Otherwise, it's not a very useful one. That's it. Okay, so we have this category, and you may be wondering, well, who cares? What's an example of this? And I guess the main motivation was the following example. It's local homology. So how you get such a thing? So let's do it here. Example, local cohomology over regular rings. Let's see, well, so this is the deal. You remember, okay, let's take R, but for now we can just take it to be a ring, and we can take an ideal. And so we can even take a module N, right? So an R module. And so out of this data, we can construct these beautiful modules that by definition, if you want, or not by definition, but by definition actually, it's not too surprising. There's going to be a certain limit over this X. Right, so you remember this? I'm confused again. So the point is that right, if you have these portions, this is gonna look like yeah, R modulo A. Sorry, it's like this, right? So in principle here, this system here goes like this. But then when you take this, pointer, X into N, the arrows are reversed. Then what did I write limit? I'm confused again. One sec. So R modulo A. I'm confused as for why I wrote limit here. Should it be a co-limit? We had this discussion already when we defined when we saw this. Oh no. Yeah, this is a co-limit. Yeah. The point is that the arrow goes like this. Because the arrow, yeah. So you see that when you look at this system here of portions, they go like that. They just get bigger. Then when you take the functor, the arrows get reversed, and then what you do is take this limit, which technically speaking the co-limit. Yeah, sorry, just had a little confusion again. Okay, so we had that. And however, this can be computed using Frobenius instead. It's something I think we haven't said yet, but we should have. So the point is that if A, let's say, is generated by how many elements? Let's say k elements. And we see the following. So let me get the numbers right. So it's the standard way in which you can compare Frobenius powers with ordinary powers, right? So this one is supposed to be rather trivial, right? Because this, if A is generated by, let's say, A1 through AK, well, A to the Q is going to be generated by A1 to the Q, blah, blah, AK to the Q, right? So definitely this is inside this power. So the Frobenius power is deeper. So it's contained there, but not by much, right? So this is a pigeonhole principle. If we have k of them and we take this sufficiently large power, an ordinary power lands inside here. Okay, it's just a pigeonhole principle. Let you think about that. And so what this means is that this exact same limit can be computed by the following. So it's a very classic trick. So then this local cohomology module is going to be equal to the limit. Now, what I'm going to do, instead of using ordinary powers, I'm going to use Frobenius powers, because they're in sandwich like that. Okay. Now the limit is over E. So just remember, Q is P to the E. That's the first observation. So let's put it here. So, and yeah, this is one of the key equalities to study local cohomology using Frobenius. So the second observation is, what is the pullback along Frobenius of a quotient module, of a cyclic module? So here you have a cyclic module. It's a module generated by one single element, therefore it's isomorphic to R modulo A. And so how does this work? Well, so this is well, here again, what is slightly annoying is like the source and target of Frobenius are the same. But let's do the general case, right? If you have a ring homomorphism, and which gives you an F, right? An F going on a spectrum like this, spec R, spec S. How do you pull back a module that is R modulo A? Well, this is S tensor R modulo A. What is that? It's S tensor AS. Right? So pulling back a single module work like that. And so here what we're going to have to do is to take the extension of A along Frobenius. And that has a special name, right? The definition of that extension is the Frobenius power. So here we're going to have R modulo A to the Q. Right? If you want, this is the definition of this thing. So we have that. And so what that's going to imply is the following. So we can look at this quotient here, and then we can compute its pullback. Well, we can compare it versus its pullback. But we just learned that this is our A PQ, right? This thing here is P into 1. Remember, this is P to the A. And therefore, we get a map. That's my whole observation here. But if I have a modulo that looks like this, it admits a canonical map to its pullback. The other way around. It's like that. Like that. Because you know what I'm going to do? I'm going to take x right after this. So, okay, so okay, yeah. So the point is that when I look at the sequence here, let me do it in this, right? So let me do A to the P, right? So this is R A to the P squared. R A to the P cubed. So my observation is that what these objects really are just the pullback of Frobenius of this thing. Yeah. Okay. I guess that's my second remark. But what happens if we apply x to that? Forgetting to know this. What happens if we apply x? Now, when we apply the x functor, the arrows go the other way. Here I'm going to use R now. You will see why in a second. I'm going to apply this functor. Then we're going to get a chain that goes like this. I'm going to use pullback here. And then the second one is going to be this one. So on. Wait, let's continue here. So on. Is everyone with me? Now I got the arrows in the direction I want them to be. But I guess I wrote I just read the definition of the object I want to have. Right, so you get this sequence of things. Now, look at, maybe I need to move the camera again. Now look at what is the object here, right? That we're going to have x, I, R of the pullback. Let's say the yeah, so let me write down with this. This is slightly annoying. I started in the. I should have started differently. Well, what I wrote is true, but you see what I really want, right? No, I can't even move the camera. Sorry, let me fix the numeration of things. It doesn't matter because I guess we're taking a limit, but it matters for to calculate the root. I hope in the notes I didn't make the same mistake. Same mistake in the notes. Okay, so I should have started, so let me correct myself. I should have added here R modulo A, and this object here is the pullback of R modulo A along forbiddeness. And yeah, this one here should be the second one of this one. This one here should be the third one of R modulo A. Okay. So I guess here I could have added another term, which is the zeros term. Okay. And so here I should have written pullback of this, second pullback of this, and so on. So the point is that, yeah, this is what I want to write, sorry. So it's a limit over this object. Okay, it's just like, so that, yeah, so just to repeat myself, so we should have started with a sequence that is like this. Because this is R a to the P, and this is R a the P squared, and so on. So when you take X, here you're going to have X R modulo A, R mapping into SI pullback of R modulo A, R X R second pullback of R modulo A, R, and so on. So the ETH term should look like this. Okay. So now my third remark is the following. So let's look at this object, and this object here is going to be equal to the following. And here I really need you to pay attention to this, because I'm going to use for the first time in a key way that R is regular, and so that this isn't a flat. Forbiddeness is flat, and therefore the pullback is exact. Therefore, commute with cohomology. So it carries no cohomology, therefore it commutes with any cohomology functor. So it's going to go out. It's a trick that we have used before. So this thing here, because R is regular, is naturally isomorphic. So I'm going to write it down as an equality to the pullback of X of this thing. And there you are. This is going to be your n. This is the root of your local cohomology module as a eulerstic module. I just show you that the local cohomology module, it is a limit, a co-limit over the pullbacks, over the Frobenius pullbacks of a very specific module. That one, right there. When R is regular. When R is regular. Okay? Because of Kunz's theorem. Okay? So is that okay? Do I need to give more details? That's your root. And so what you see here is that right, what's going to happen? That this guy now is going to be the pullback of S I R modulo A, comma R, right? And you keep doing that. And so this is your gamma. This n and this n and this map here is your root, whose limit is going to give you the divesting module by definition. So this is the key example, I guess, that motivated divesting to hook up this definition. Okay? So there are examples and important ones. Okay, now I'm going to construct a new set of examples. I'm going to tell you how every Cartier module defines a divesting module naturally. Okay? Remember the goal. The goal is to prove that local cohomology modules over regular rings have finitely many associated primes. So the first thing is to observe that actually they are divesting modules. And so it's divesting modules who have this property. Okay? And so to see that, we have to connect them to Cartier modules. So that's the next step. Are you with me so far? Okay. So okay, Cartier modules next. For that, I'm gonna start giving you an exercise that I had given you a long time ago, but this is the first time we did it, so I guess it makes sense to do it now. So, remark / exercise in the notes. So far, this is exercise 6.21. And so it's just abstract nonsense. Let me see. Yeah. So we're going to start with a ring homomorphism, just a finite flat extension of rings. And so you remember we denote by S the corresponding map on the spectrum. And so look, we have a canonical map. Let me write it down. From here. So here I'm going to take any module. So this is an R module. Here. How does that work? Well, I need to tell you where to send a map here. So let me take a map here. Let's call it sigma. And let's take an element M. Okay, how do you pair them together in a bilinear way? Well, I have to send it to something that is a map from S to M, right? So I'm going to take S, and the point is that S cannot act on M, right? Because M is an R module. But if I have a sigma, I can take that S and make it an element of R. So I can take sigma S, now it's an element of R, and therefore it can act on M. So I can just do this. Okay? And so there is a canonical map like that. So, and what is the exercise? What I wrote doesn't need anything, right? I'm going to use now these two properties here. So, this is an isomorphism when F is finite and flat. Okay, but what are these things, right? You gotta recognize them. This is the upper streak of R. In the same way, this thing here is the upper streak of M. And the whole thing here is pullback. So a more abstract way to say this is that we always have a natural transformation from these two functors. I hope it's clear what this functor is. You pull back and then tensor by this. So there's a natural transformation from this functor to this one. So I'm saying that this is natural on M. Okay? Oh, F upper streak. And when F is finite flat, this is an isomorphism. In other words, when you have a finite flat extension, upper streak is completely determined by pullback. That's it. Okay? So that's your exercise. It's a very important thing to know about, actually. It's a very important trick. Actually, right now I'm writing a paper that is just based on that trick. With a different setup for more general maps, but much more general maps, but that's the trick. That upper streak usually is the one with the good properties, but sometimes the pullback is what you need. And so instead of setups, you can replace F upper streak to pullback, showing that pullback has good properties. That's sort of it. So okay, so you got that. Actually, you may remember that we had a name for this module. It was the relative canonical module. The canonical module of F. Canonical modules are things that are intrinsic to maps, are relative objects. So, I'm gonna choose a chart. So we can be slightly fancier and write that what we have is a natural transformation from here to here. So for example, if you know about local Gaussian, you would see that this is a typical thing for a smooth morphism, right? Saying that this is flat is just saying that this is going to give you, well, not quite smooth actually. But this is a property for a smooth morphism that the F upper streak is given by pullback tensor with the relative canonical. It's just that. So, but if this fix it up, it's a much simpler thing to do. So, okay. In particular, what do you think I'm going to do next? If R is regular, and F finite. Remember, this is a hypothesis we said that we're going to be assuming all the time from now on. Then we get a natural transformation like this between Frobenius pullback and F upper streak. Okay, so I need you to keep this in your hearts for a sec. Move the camera a little bit. So the next thing to do is the following. So let's recall how the Cartier operator was defined. So recall that we had an adjoint relationship, just like this. And I guess here we had this one too. So, but this adjoint here is just means that if you have column R, Well, it's much more general than this, but in particular, it says that these two things are the same thing. Okay. So remember that, yeah, this thing here, this adjoint relationship, it's just a formal mathematical way to express precisely that this object and this object are the exact same thing. They carry the same data. So if I give you a Cartier operator, right? A Cartier model here, it's supposed to be the same data as this. Okay? And so actually, what we said is that if we have an isomorphism from here to here, right? That was part of the hypothesis to construct the Cartier operator. You remember? It was a weak hypothesis because it holds in the local case and for varieties, right? But under this assumption, then this is going to be adjoint or represent the same object as a Cartier operator. Okay. The Cartier operator is adjoint to this hypothesis, essentially, thanks to this. But much more generally, a Cartier operator, a map from here to here, is the same thing as a map from M to F upper strip. Okay, we good? We're just recalling things from now. Now, what I want to do is to understand what this thing here is. We have done it before, but let's be a bit more explicit. So next remark is that R is regular, right? That's the case in the curve out, and therefore it is Lorentzian. And so we can write Lorentzian normal, this, like this, where this is a Cartier divisor. So I'm going to write the inverse of the canonical divide. The canonical module is often referred to as the anti-canonical. This is the anti-canonical module. It's by definition R negative K. Okay. This is how I'm going to write it. Okay, so let's come back to this. And in particular, I can plug in the canonical module in there. Right? So if I plug in the canonical module, I'm going to have something like this. The assumption is that the upper shape of omega r is omega r, so I'm going to have omega r over here. And so let me keep going this. What is the conclusion? The conclusion is that this natural transformation here really becomes omega r tensor, maybe like this, pull back the anti-canonical tensor blank the one. Essentially, i.e., all I'm saying is that omega f equals, according to this, omega r tensor pull back of omega r inverse. Okay, that's what I'm saying. And so I have just on route what it means to appropriate by Frobenius. That process is naturally the same thing as doing this. First, tensor by the anticanonical. Apply the Frobenius pullback, and then apply tensor by the canonical. Okay? Yeah. I cannot stress enough that this is just pure nonsense. There is not much to go into it. So, which I guess is the beauty for the project, right? It's just nonsense at the end of the day. Abstract nonsense. So, then, if I have a Cartier module, right? That's the Cartier module interface. By the adjoint relation, it is the same data, or it is adjoint to n f approximate n, right? Which you can compute explicitly, right? If you know the units and co-units of that, you can compute that. It's very explicit construction. So you can construct this, but now when R is regular, we know very well how this works. It's right there, right? So this thing here, I'm going to write down equal because it's naturally isomorphic. So it's going to be isomorphic to this. But this is a Cartier module. Sorry, this is. Well, the canonical divisor is a Cartier divisor, and therefore this is invariable. So I could twist by omega r inverse to get rid of this in here and move it to the other side. So, moreover, this is the exact same data as a map from omega r inverse tensor n to pullback of omega r inverse tensor n. That's your root. Okay, and then now you can take a limit over that. That's your gamma. So literally, the information contained in a Cartier structure over a regular ring is the same information as the information of a root. Okay? So, let's move to the other side. So, oops. Yeah, so in other words, let me just sum up again. If you start with a Cartier operator or a Cartier module, let me call it kappa, over a regular ring, this is none other than a map from here to here, let me call it gamma. So this is a root in the limit that's going to give you, well, I guess an n to here. So this thing from here to here, it's something that Libesky called Jan, I think, in his paper, but let's just call it L, vector of the Libesky functor. So we got a functor from the category of Cartier modules over regular rings to the category of investing modules. So literally, any Cartier module is going to give you a investing module over a regular ring, as an example. So I just gave you a billion examples. But moreover, over a regular ring, these are the only ones. Because let me give you an exercise. It's an exercise that I think is wonderful for you to think about, because it's going to make sure that you understand the definition of everything. Exercise. This functor here is essentially surjective, meaning any logistic module is cooked up in this way. It is. It is an easy exercise, but it's just writing down what everything means and saying yeah. Okay? It's essentially surjective. No, what is the name? It's essentially surjective? It's called like that? Yeah. Well, I guess, yeah, well, the essential image is the whole category. So let's say essentially surjective. Yeah, I think people say this. In other words, all the vesting modules are obtained by this process. That's the intuitive way to think about it. Can we lose information in this process? They're going to be a good guess at this point. What is the information that can be lost? Nilpotency. If you start with the nilpotent Cartier module, you get the zero divesting module. Okay? If you have the nilpotent Cartier modules, remember that this form a subset category here. That is the category we use to localize this category to get the Cartier crystals. So this whole subset category goes to zero. It collapses to the zero divesting module. Notice, zero is a divesting module. Zero, the zero module, I mean the math, so it's pulled back because its pullback is zero. And that's an isomorphism. It's just so that happens. So what that means, very formally, if you have a functor from a category to another category, and that kills a subset category, automatically that induces a map from the localization to the localization. So this means that what you really have is a functor from Cartier crystals to Levesque ones. But moreover, any guess what happens to this? To this? This is an equivalence of categories. So theorem, let me put it here. This is just an equivalence of categories, not an isomorphism. That's a different thing, right? So how do you denote an equivalence of categories? Well, whatever. So theorem. This is an equivalent. This is the semi-divesting functor. It's an equivalence of categories. In other words, look at it, right? Over regular ring, we can be very explicit about what the Cartier crystals are just divested modules. Actually, I hope you agree that this is more explicit than what this is. This is actually kind of constructed by definition. It tells you what it is, instead of doing some crazy abstract nonsense, right? But at the very least, for regular rings, we get this. In particular, we get to prove that this is a special category for the category of two models thanks to this isomorphism. Actually, you don't need this one. You just need that is this rejection to do that. For which you need regularity, right? To have this rejection. So unfortunately, this equivalence is not it's not as easy. I thought it would be much easier, but some details I will have to get into much. We will have to really to understand how this construction works and do a whole bunch of things. It's not difficult. It's just abstract nonsense, but intuitively is what you expect it is. Essentially, the information. So intuitively, it means that the information you lose when you go from here to here is literally an impotency. Okay? What you have to prove in principle is that, yeah, literally what this means is that if two Cartier modules, that two Cartier modules are nil isomorphic, if and only if they use the exact same investing module. That's what you have to prove. The way you do that in practice, well, when you do the proof, I wrote a little bit of the details in the notes, is that when you look at the basic module, you know that it has a root by definition, right? It is built out of a root. This n gamma to pull back n. But there could be many roots. What you really have to prove is that all those roots has to be nil isomorphic to one another as Cartier modules. When you look at the Cartier modules that define them. Okay? So but actually we don't need the whole equivalence for what we want, right? What is enough? The surjectivity, right? So this essential surjectivity for what we need, which is the following corollary. So for now, I don't want to give the details of the equivalence. First, because it's going to be more time, and we're already running out of time today. So maybe at some point I'm going to add the details in the notes. And well, also because we only need the surjectivity for the following corollary, which is that the category of the events and modules have finite length. The objects there have finite length. Okay? Because it's even smaller than this one, which is already very small. Okay? So where is it? So over here. Corollary, if we have a regular ring, regular and finite. By the way, this thing here, I'm gonna. So actually, this category here of the vesting module, essentially have an analog to characteristic 0 and so on. But you need to use V modules. That would be the thing and so on. But for positive characteristic, we have this. We have a regular, a finite ring. Then Lubeznik modules have finite length. B. And what this is what we really need here. The Lubeznik modules have finitely many submodules. What Lubeznik submodules? So in this category, any object has finitely many sub-objects, if you want to be very abstract. And then we have this absolutely glorious corollary. we have our regular, then this has finite many associated primes. Well, let's think about it, but the point is that the associated primes of these objects this is a linguistic module, so it has to have finite many associated primes because well, there are many ways to see it, but geometrically speaking, what's happened, you have a linguistic module, and it's going to be supported somewhere in many different components. And each of them have to be finally many. It's because, so when you go and look at, so you have your object geometrically speaking, so you have your module, which is this one, and it's going to have many different components. And so the point is that how you can hook up these sub-objects, so you can then restrict M to every single component, and that's going to be surjective. And then the kernel is going to be a sub-object, and those sub-objects are the ones that are going to give you. So every single associated prime is going to give you a sub-object by this process, and those sub-objects have to be finite many. Okay. Another way to see it more explicitly, actually, is that the root of this thing was this Noetherian module. And this one has finitely many associated primes, and actually by this sort of equivalence, it has to be the associated primes of this one. That's okay. So that's the application I wanted to give you. You may have noticed that all we have done so far is pure and complete abstract nonsense, right? The math has to be somewhere, right? Math is not for free, right? What are we missing? This whole nonsense comes from the existence of test modules, right? The category of Cartier crystals is only finite because of the existence of these test modules. And we have used that in a straight change of pure abstract nonsense to conclude something very difficult to prove. This was a major open problem for decades, right? And so if we haven't proved anything, right? This proof so far only says that this thing is a formal corollary of the existence of test modules, right? And so what we're going to do next is prove that. So next week, I think for the whole week, we're going to spend both lectures just proving the existence of test modules, and definitely proving this. Okay. But I hope you appreciate the approach, which is very algebra geometric. You really try to isolate what is pure abstract nonsense, so that you can distill, you know, where the problem really lives. And then you do that. Okay. So I guess we can stop here for today. I don't think it makes sense to start in here right now. Okay, goodbye, people of Zoom.
Thank you. See you next week.
Bye bye.